All right, so 11.1, sequences and summation notation. All right. All right, so definition of sequences: an infinite sequence is a function whose domain is the set of positive integers. The function values or terms of the sequence are represented by a sub 1, a sub 2, a sub 3, all the way to a sub n. And remember, this is infinite sequence, so you're talking about on to infinity. Sequences whose domain consists of only the first n positive integers are called finite sequences. In other words, they have an end. All right. Of course, if I scroll up too much, feel free to let me know. All right, the first exercise, write the first four terms of the sequence. Here we have a sub n is equal to 3n plus 4. So A sub 1 means you take 1, plug it in where you see n. That's going to be 7. Let's see, do I want to write it any other way? No, that's good enough. A sub 2, 3 times 2, that would be 10. 3 times 3, 13, and then A sub 4, 3 times 4 plus 4, 16. All right, questions about that sequence? All right, so for B, we have A sub n is equal to negative 1 to the nth power over 3 to the nth power minus 1. So make sure we're careful with our n's and our exponents and all the good stuff like that. So A sub 1 is going to be negative 1 to the first power, 3 to the first power minus 1. That would be negative 1, 3 minus 1, which is 2. So that'd be a positive 1, negative 1 squared. That's 9 minus 1, which is 8. So notice in this case, we're going to alternate signs because we're raising that negative 1 to a power. Negative 1 cubed, that's 3 cubed minus 1 on bottom. So that'd be a negative 1, 27 minus 1, negative 1 over 26. And the fourth one, it was positive 1 on top, 81 minus 1 on bottom. So 1 over 80. All right, any questions before we go to the next one? All right, so the next thing is the recursion formula. It defines the nth term of a sequence as a function of the previous term. All right, so here we have write the first four terms of the sequence in which they give you a sub 1. A sub 1 is equal to 5. And then a sub n is 3 times a sub n minus 1 plus 2 for, and look at the domain of n, for n is greater than or equal to 2. So this sequence starts, when you talk about plugging in, it starts with plugging in 2 because they already gave you a sub 1. So now if they say write the first four terms of the sequence, the first term of the sequence is given. So a sub 1, 5 should be that first term of your sequence. Then a sub 2 is going to be 3, and the way you should look at it as 2 minus 1 plus 2. So it's going to be 3 a sub 1. Yep. I wrote it down a little lower than I needed to. There you go. There you go. 3 a sub 1 plus 2. And we saw that a sub 1 is 5. So that's 3 times 5 plus 2. That's 15 plus 2, which is 17. All right, do the same thing for a sub 3. That's going to be 3 minus 1 plus 2. That's 3 a sub 2 plus 2. A sub 2 is 17. That's 2. So there should be 53. It's 51. Yep, 53. And the last one, a sub 4. And you know, even if you don't write that second step, that's how you should be processing what's going on. So a sub 3 was 53. 51, 57. Oh, I get 57 from missing a spot. That's right, carry that. 61. 59. I get that. Yep. All right, questions. So once again, if they ask you to write the first four terms, your first term is a sub 1. So make sure you don't go to a sub 5. You know, then this will a2, a3, and a sub 4. So everybody okay? Not too bad, right?
So far, so good.
Think you guys will be all right. So factorial notation, just in case you may have forgotten, or maybe you haven't seen it, or maybe you haven't seen it in a while. Exclamation point in mathematics is your factorial notation. That means you would take that number, continue to subtract 1 from it, all the way down to 1, and multiply those numbers to each other. So if I had 100 factorial, I'm going to do 100 times 99 times 98 times 97 times 96, all the way down to 1. So 1 factorial is equal to 1, of course, but also 0 factorial is equal to 1. And there is a proof for that. Yep, so 0 factorial is equal to 1, and 1 is factorial is equal to 1. And just a mini example, if you have 4 factorial, that's 4 times 3 times 2 times 1, which would be 24. All right, so we want to write the first four terms of this sequence. We have a sub n is equal to 2 to the nth power over n minus 1 factorial. So plug in 1 for n. 2 to the first power is 2. 1 minus 1 is 0 factorial. It's 2 over 1, which is 2. Next one, plugging in 2. That's 2 squared, which is 4. 2 minus 1 is 1 factorial. So 4 over 1 is 4. A sub 3 is 2 to the third power. 3 minus 1 factorial. It's 8 over 2 factorial. 2 factorial is just 2 times 1. 8 over 2 is equal to 4. The last one, 2 to the 4th power, 4 minus 1 factorial. So 2 to the 4th power is 16 over 3 factorial. 16 over 3 times 2 times 1. 16 over 6. And that reduces to 8 over 3. What about this? All right, questions. All right, so giving us more factorials to evaluate. Let's say we start here. A factorial over 5 factorial. Just want to make sure we're seeing this properly. So if I want to simplify this, this is 8 times 7 times 6, 5, 4, 3, 2, 1. Factorial, 5 factorial is 5, 4, 3, 2, 1. So now we know how fractions work. Since all of this is multiplication, I can cancel out 5, 4, 3, 2, 1, because that's what I have in common with the top and bottom. And that leaves me with 8 times 7 times 6. This is down here. Which I believe is 336. If I'm not mistaken. I want to make sure before I keep going. Yeah, I'm good. So now, when I look at that, what we don't want to have to do is always list out every number in order for us to see the relationship. So if I have 8 factorial over 5 factorial, being that 8 is greater than 5, I recognize that in this 8 factorial, there is 5 factorial, 5, 4, 3, 2, 1. So I just recognize that, and I can go ahead and cancel out the whole 5 factorial, and that still leaves me with 876, which is 336. So if that option is presented before us, then we want to take advantage of that, because if I have something like 100 factorial over 98 factorial, what I don't want to have to do is write out 100 numbers on top and then 98 numbers on bottom to recognize the relationship that they're going to cancel out some things. So I just go 100, whether you write it out or not, we're doing 100 times 99 times 98 factorial. because we have 98 factorial down bottom. They cancel for us, and that leaves us with just 100 times 99, which is 9,900. All right. So questions on those before we look at other scenarios that they give us. That's the thought process that you want to have when you're looking at canceling out factorials that's on top and bottom. Same thing as if I had, let's say, I don't want to go that high. Let's say if I had 5 factorial over 3 no, I don't want to go over, let's go here. 3 factorial over 5 factorial. In other words, the greater number is on bottom. Well, I know it's going to be 5 times 4, and then stop at 3 factorial. Oh, lost my pen for a second. They cancel out, and if everything cancels, of course, you're left with the 1, so that's 1 over 20. So it can happen the other way, you know, in which what's in your denominator is greater than what's in the numerator. But that same thought process holds true as far as canceling out everything that decreases all the way down to 1. And you go from there. So now if I had something like this, ten factorial over 2 factorial times 8 factorial. So what we want to hold true and make sure we recognize is that first off, you can't do 2 plus 8 factorial in the bottom and get 10 factorial. Neither can you do 2 times 8 factorial and get 16 factorial. Those are 2 different factorial applications. So one of them you're going to expand, and one of them you're going to be able to cancel out. Just, you know, you make a decision which one you're going to go with. Of course, you should go with the greater. So in other words, this 10 factorial goes down to 9 and to 8 factorial because we have 8 factorial down bottom. And that 2 factorial, you would actually expand it out. You know, it's possible you could have something greater than that. So if I had 4 factorial times 8 factorial, then I would do 4, 3, 2, 1. I would go ahead and expand that out. And so my 8 factorials will cancel. And this 2 can actually cancel into the 10 and leave me with 5. So what we're left with is 5 times 9 in your numerator and then just 1 down in your denominator. So that would be 45. Another way of doing it, the way the book did it, just saw the way they did it. They canceled out 8 factorial and left it at 10 times 9 over 2 times 1, which is 90 over 2, which is still 45. So if you want to cancel that 2 out into the 10 or just do it at the end, either way, it will reduce down to 45. But the main part of the application is to cancel out, or the evaluation is to cancel out the 8 factorial to make things simpler on yourself. All right. So the next one, you have to think generally, because they don't give you numbers. They give you n plus 1 factorial over n factorial. So let's go back to how the factorial is set up generally. Here it goes. Notice you start off with n and then you subtract 1. So it's n minus 1. They subtract another 1, that's n minus 2. Subtract 1 again, n minus 3. So then it'll be n minus 4, n minus 5, all the way down to 3, 2, 1. Right? So that's what's happening here as well. You have n plus 1 factorial over n factorial. So what I can do is recognize that the next step in this n plus 1 progression is to subtract 1. So in other words, and I'll write it down here. When I look at n plus 1 factorial, the first thing that will be written in the sequence is n plus 1. Then you subtract 1, that's just going to be n. Then you subtract 1 again, n minus 1, n minus 2, all the way down to 3, 2. Well, I could just write 2, 1. All right. So, but what the key in this relationship is that right here is our n. So what I can write as far as my sequence is concerned, n plus 1 times n factorial, because down bottom I have n factorial. And remember, n factorial is n minus 1, n minus 2, n minus 3, all the way down to 1. And they're going to cancel for me and leave me with just n plus 1 as my answer. All right, questions on that one? All right, let's say if I had n factorial over n minus 2 factorial. So I would take that n factorial down to n minus 2. Because remember, you can keep subtracting 1 until you get to that. N minus 2 factorial will cancel. And that'll leave you n times n minus 1. Or if you wanted to distribute, that'd be n squared minus n. So either one should be fine. All right. Any questions? All right, one more thing out of this section. I'm certain on where those end terms will end without the ellipses. Oh, well, as far as they would tell you, that's the difference between a finite sequence and infinite sequence. If it's infinite, and we're gonna talk more about that. I think 11.2. Let me look at arithmetic sequences. But for the most part, if it's going to end, they will tell you what the end is going to be. That's why they keep saying like the first n terms or whatever. But if there is an infinite sequence, that will be stated as well. So the sum of the first n terms of the sequence is represented by all right, so before I go scroll up, summation notation is the sum of the first n terms of a sequence is represented by the summation notation, where we have Greek letter sigma capital letter sigma. And then we have a sub I. And I would be equal to 1 in this case. You can start it wherever you like as far as your summation is concerned. And you would just plug in the values the same way we did our sequences. It's just that now with the summation, we're going to add those terms together versus just having our terms listed. And so that sigma lets us know we want to add our terms together. So I want to use black steel, is index of summation. Right, it should be an N up here. Let me do this. I left off N up top. And so point it like that. All right, so I is the index of summation. That's the letter that's going to change throughout. It will start with your lower limit of summation, which in this case will be 1. That 1 that's down bottom, I is equal to 1. That's where it starts. And then your upper limit of summation, upper limit of summation is N. That's where your terms will end. So you'll see in the next example. All right, so we want to expand and evaluate. All right, so for the first one, we have the summation of 1 to 6, or the summation from 1 to 6 of I squared plus 1. All right, so I have room, bring it down here. So plug in 1, plug in 2. I'm gonna run out of room. So you just plug in 1, 2, 3, 4, 5, and 6. So 1 squared plus 1 is 2. 2 squared plus 1 is 5. 3 squared plus 1 is 10. 4 squared plus 1 is 17. Then we have 25 plus 1, which is 26. And 37. And that'll be 97. All right. Problems with A before we look at B?
No.
Sounds good. Thank you, sir. All right, here we're looking at the summation from 4 to 7 of -2 to the k power minus 5. So it's -2 to the 4th power power. And then 7. Yeah, I think I'll write that out. So that's going to be positive 16. So make sure you're careful with those signs. That's going to be negative 32. That'll be a positive 64. And then negative 128 minus 5. So once again, just make sure you're careful with those signs when you look at problems like this. So we're looking at 11 plus negative 37 plus 59 plus negative 133. And negative 100. All right, one more like this, just in case you were to see something of this nature. So here we're looking at the summation of 3 from 1 to 5. Now notice there's no I. You know, we don't have I sitting back here as an exponent or a regular variable. So really the only thing that can happen is for first term, you have 3, second term 3, third term 3, fourth term 3, and fifth term 3. So every time you have a term, all you can do is, you know, express it as 3 because there's no variable to plug in for. And your answer is going to be 15. All right. Questions? Any questions?
I've got none.
Let's see. It may ask you to, for the last thing, it may ask you to express and go through the process in reverse. So this is what I mean by that. Express each sum. All right, we have 1 cubed plus 2 cubed plus 3 cubed all the way to plus 7 cubed. And we want to express that using summation notation. So we notice what is changing here is the base. We got 1, 2, 3, and we assume it's going to 4, 5, 6, 7. But the exponent is staying the same. So what we can do is start off with our summation. And if we let I be our variable, let 3 just be the exponent that's going to stay stationary, then we can go I is going to start at 1 and then end at 7. Questions on that one? All right, let's look at one more. I'm trying to see how I want to end this without giving you the answer. Well, I'll just write it up here anyway. All right, so the way they wrote it in the example is 1 plus 1 over 3 plus 1 over 9 plus 1 over 27 plus ... plus 1 over 3 to the n minus 1 power. So to me, whenever they do this right here, they're pretty much giving you the answer. If you were to let n be equal to 1, n minus 1 is 0. So 0 for your exponent would be 1. Any variable, any term raised to the 0 power is going to be 1. So that's how you get first term. And then 2 minus 1 is going to be 1. So that'll be 1 over 3. Then plug in 3 here. 3 minus 1 is 2. So you get 9 down here and so on. So really, they give you the answer when they give you this in the back. I was trying to figure out a clever way of not doing that. But so when I look to write using my summation notation, let I be equal to 1. Right, this here. And since we have an n right here, then I write n as my ending term, my upper limit. All right. But questions. All right. So that is 11.1. Homework should be in there. So, but what I need to post for you guys is that test review for last chapter. So I'll get that hopefully by tonight. But so before we close out today, questions on 11.1. Everybody good.
I've got none.
All right, thank you, sir. Appreciate it. Sounds good. Thank you, ma'am. So we have 11.2, 11.3 to do, and then we'll be in a great place. So outside of that, you guys have a great day. Be safe, and I will see you on Thursday, same time.
Take care.
All right, you do the same. Thank you.